Today we are going to discuss about electrostatics of conductors. And every day when I am going to start the class, in last class what we discussed that I am revising and then we are continuing that, because that continuation, even when we are watching the videos, all the videos we have to see. We follow the number, then we get the continuity of the topic. In last class, we discussed some of the important points regarding potential energy of a system of single charge and the two charges in the presence of external electric field, and the potential energy of a dipole in an external electric field. These two we completed in last class. And some of the points and cases in the torque as well as potential energy we discussed. So in that, when I discuss about the potential energy of a system of three charges in the presence of external electric field, their notation is very important. So when we are taking that potential energy of a system of two charges in the presence of external electric field, so their notation V1 and V2, we use that V is the potential and V1, V2, we are using that notation V1, V2 and Q1, Q2. So V1, V2 are the electric potentials in the electric potentials produced by the points in an external electric field. And Q1 and Q2 are the charges. Then the potential energy U is equals to Q1 or V1, but in last class I used the symbol is V. V is the potential produced by the external electric field. Here V1 is also the potential produced by the field, external electric field. So Q1 V1 plus, and this is the work done to bring the charge Q1 into the field against the electric field. That work done is that Q1 V1 plus to bring the charge, another charge Q2. Here the work done to bring the charge from infinity to the point, we have the potential is that V2. So V2 is the potential due to the external electric field. So Q2 V2 plus, and again 1 upon 4 pi epsilon naught Q1 Q2 upon R. Here the important thing is Q2 V2 plus 1 upon 4 pi epsilon naught Q1 Q2 upon R, and this is the total work done to bring the charge from infinity to the given point. Here V2 is the potential produced by the external electric field, and here the work done is between two charges Q1, Q2 separated by the distance is R. So work done to bring the charge Q1 into the external electric field is Q1 V1 plus total work done. To get the total work done, we use Q1 V1 plus Q2 V2 plus 1 upon 4 pi epsilon naught Q1 Q2 upon R. In last class I use the notation here V and here also V, and you may get doubt. It means that V is the common term. Then Q1 plus Q2 of V plus 1 upon 4 pi epsilon naught Q1 Q2 by R we may write. But you should not write that. So that again I am explaining you that here the V1, V2 are the potentials produced by the external electric field. Okay, don't think that the potential here, the potential here, the potential is same. So that different notation V1 and V2. Okay, so this is the potential energy to bring the charges or to assemble the two charge configuration with separation R is the potential energy. And one more is that here this potential energy, the potential energy is the characteristic of the electric field, and it does not depend in which way we are achieving. It doesn't depend on it. Okay, so that is also another important. And one more is that the positive charge has higher potential energy at higher potential, and the negative charge has the lower potential energy at higher potential. That is also one of the important point. And the potential energy of a dipole when it is placed in a uniform electric field, so that U is equals to, we have got minus P bar dot E bar. This is the potential energy. Potential energy when the dipole is placed in a uniform electric field. So when the dipole is placed in uniform electric field, it doesn't experience force. It experiences only the torque, because we know about the torque. The two equal and unlike charges separated by a small distance, and the line of action of force is not same, then it produces the torque. Whereas the force, when we come to the force, the direction is opposite, magnitude is same, the net force is zero in case of uniform external electric field or uniform electric field. If you say simply, is that uniform electric field. And here we have the cases I explained in last class. When theta equals to 0, when theta is equals to 0, what happened to the potential energy cos 0? Here the dot product gives that cos component. Then cos 0 will be 1. Then potential energy will be minus P, and it represents that maximum potential. It's not the maximum, minimum potential energy. And it gives the stable equilibrium. And about the torque will be 0, because in torque we get that the sine, the theta value is 0, sine 0 will be 0. If theta is equals to 180 degree, if theta is 180 degree, it means that the dipole moment and the electric field are anti-parallel. Then cos 180 we know minus 1, then it will be P. The potential energy will be P, and it will be the maximum, and it gives the unstable equilibrium. And if theta is 90 degree, it means that the dipole moment and the field, electric field, are right angle to each other. Then the potential energy will be 0, because cos 90 is 0, but torque will be maximum. Suppose the dipole is placed in external field that is non-uniform. It is not the uniform, non-uniform. So when the dipole is placed in non-uniform electric field, next point, important point is that when the dipole is placed, the dipole is placed in non-uniform electric field. So when it is placed in non-uniform electric field, what happens? We know that when it is placed in uniform electric field, it doesn't experience force. Whereas we place in non-uniform electric field, then it experiences force also, as well as the torque. And what will be the force? The force F is equals to minus del into V, and here this represents that it is the operator partial derivative. The dou is equals to dou by dou R. So here the use is equals to means that dou by dou R, or if you use that x-axis, y-axis and z-axis, then it will be dou by dou x plus dou by dou y plus dou by dou z. That is the operator, and it represents that gradient. We know that potential gradient is the dV by dr, and here the dou by dou r is the gradient. So minus delta V means that minus dou V by dou r. Okay, that represents it is equals to minus dou V by dou r. And if you take the axis along x, y, z axis, we can represent, but here we are taking r is the position vector. Then the force experienced by the torque when it is placed in non-uniform electric field is the potential gradient minus of del V is the negative gradient of the potential energy. Okay, so del V, we can write that negative potential energy, and one more is that here we use the potential energy also, negative potential energy gradient. We use the potential energy gradient, that is dou U by dou R. It represents the potential energy gradient. Okay, so then when it is placed here, we can use that symbol U because of potential energy. We write in terms of the potential energy in place of V, U we write it. When it is placed in the non-uniform electric field, if R means that the force is along the direction of the R, then the force will be the dipole. Here we can use that the dipole moment, or the dipole is along the direction of the R, then the force F is equals to minus dou by dou R of P bar dot E bar. We can write that P bar dot E bar. So when it is along the direction of R, the dipole moment P is along the direction of R, then force is F equals to minus dou by dou R of P bar dot E bar, or we write that D by dr of P bar dot E. Okay, and when it is placed in, here we can use the differential operator. It is that D by dr of P bar dot E bar. And if the dipole moment and the electric field, both are along the same direction, then force F is equals to minus D by dr of P cos theta, and there we write that F is equals to minus P into D by dr, because there the theta value is 0, then cos 0 will be 1, then the force is F is equals to minus P into D by dr. So these are the important points in case of potential energy of a dipole when it is placed in non-uniform electric field. We know in uniform electric field U is equals to minus P bar dot D bar. When it is placed in non-uniform electric field, it experiences the force and the torque also. Then force is the negative potential gradient of potential energy, and minus 2u by 2r, and here this p bar dot e bar, when the dipole moment is along the direction of r, and it is along the direction of r, then d by minus d by dr of p bar dot e bar. And suppose the dipole moment and the electric field, they are along the same direction, then the force is minus d by dr of p cos theta, and it becomes minus p into d by dr. Okay, and some more important points for the potential energy. As we know that electric field is the conservative. What does it mean? Electric field is conservative. It means that it does not depends on the path. It is independent of the path, or it depends on the initial and final points. So for that we want to write that potential difference. As we know, electric field is conservative and work done is independent of the path. It does not depends on the path and it depends on initial and final points. Then the potential difference, we write that work done from A to B is equals to the potential energy. We write from here, we can represent with the potential VB minus VA, potential difference. VB minus VA is equals to integral A to B minus E dr. This we know. Now I want to discuss with you that if the particle, the charged particle is moving from one point to another point, and those points are fixed points. The particle is moving between the two fixed points. Then what happens now? So the work can happen, work can be done till the potential of two fixed points should be same. For example, I am taking A and B are the two fixed points. A and B are two fixed points. Here A and B. A and B are two fixed points, and here the charge, that is the positive charge. And that charged particle is moving between two fixed points, and they are moving in different paths. So here this is the particle, charged particle, and this charged particle is moving between A and B. The paths are there. So here you see the path, and this is the one of the path, A to B between these two, and here is one of the path. So why I am using here that the charge is moving between two fixed points and path, different paths, but whatever the path, it doesn't depend. As we know, electric field is a conservative. But this charged particle moves between two fixed points till the potential should be same. Okay, so by showing with the different diagrams, I am explaining you till the work should happen, the potential of the 2 points should be same. And the second example is that here the point A and the point B, but the charged particle is between 2 points. The charged particle is between two fixed points, and now the path of the particle is one will be along this direction. These are the two different paths, but the work done will be same because it does not depend on the path. Okay, till the potential should be same. Okay, these are the two different points, different examples to get the potential. How long work should happen when the charged particle moves between the 2 points. And the next one is that one more also. If you take the different paths, it doesn't depend, but it will move from one point to another point till the potential is same. And when the charged particle is accelerating, then we know according to work energy theorem, work done by the forces, that work done is equals to the change in energy, and here the energy is that we write Q of VA minus VB, potential difference between the points A and B. So according to work energy theorem, that work done by the force is equals to Q of VA minus VB, and their work done is equals to the potential energy. The change in, we can write that potential energy is that half mv square minus half mu square is equals to Q of VA minus VB. Q of VA minus VB, that is the energy. Potential difference is equals to the change in kinetic energy by using the work energy theorem. And now here that if the potential difference of VA minus VB, initial point is 0, if you start from origin, then the kinetic energy is half mv square minus half mu square is equals to qv. Or another way also we can say, instead of taking the potential difference, here the work done is equals to the charge into the potential, and this is the change in kinetic energy. Work done by all the forces is equals to change in kinetic energy. If you use that formula, the change in kinetic energy is equals to work done is Q into. And now if you simplify, we want to know that what is the velocity of the charged particle, and to get the velocity of the charged particle, so here the final velocity half, we take the common term is half m is the common term, then v square minus u square is equals to q into v. Then v square minus u square is equals to 2 into q into v divided by m. Then v square is equals to u square plus 2 into qv divided by m. Then v is equals to root over u square plus 2 into qv divided by, and this will be the velocity of the charged particle when it is accelerating. When the charged particle is accelerating, then the final velocity of the charged particle is v equals to u square plus 2qv by m. And if suppose if the charged particle starts from rest, then what happens here? The initial velocity becomes 0. That if the particle starts from rest, we know that initial velocity is 0. So when initial velocity is 0, then if you simplify that formula, then v is equals to root over 2 into qv divided by m, and this will be the velocity when it starts from rest. Suppose the particle is moving in uniform electric field. Here this will be either uniform or non-uniform electric field. When the particle is moving, it means it is accelerating either uniform or non-uniform, then the velocity v equals to root over u square plus 2qv by m. So here v is the potential and here v is the velocity, final velocity, and u is the initial velocity. If particle starts from rest, then initial velocity 0, then v is equals to 2q by m, and here this v represents potential, electric potential, not the velocity. And if it is the uniform electric field, we say that either uniform or non-uniform. In terms of uniform electric field, we can write in terms of electric field that potential, as we know the relation between electric field and the potential E is equals to V by D. E equals to V by D. Then potential V is equals to E into D. And if we substitute, then the final velocity V is equals to 2 into Q into V. We write that ED by M. And this will be the final velocity of the charged particle when it is moving in uniform electric field. Uniform electric field. We know that while discussing relation between electric field and the electric potential, there we know E equals to minus dV by dr. If the field is uniform, then E equals to magnitude of the electric field. E is equals to V by d. That we substitute in this formula, then final velocity we got it. And one more is that we know potential energy generally for the molecules in atoms we use to measure the energy electron volts. Potential energy we measure in electron volt. So that what is electron volt here? That we are using that electron volt. What is electron volt? So to get that electron volt and the charged particle is accelerating, to gain the energy through the potential difference is 1 volt. The electron is accelerating, to gain the energy through a potential difference is 1 volt. Then the energy is potential energy is that 1 electron volt. Okay, I think so you might studied about the electron volt, but again we are discussing because this electron volt we use in potential energy concept, the potential energy of system of charges. Okay, and here the electron volt, some of the points about the electron volt. The first point is that electron volt is a unit of energy. It is unit of energy, but it is not the unit of the unit of potential difference or volt. Electron volt is the unit of energy, that is the unit of energy, potential energy we are using particularly. So unit of energy, but it is not the unit of either potential difference or the volt. And one more is that the second point, important point is that electron volt is not the standard SI unit of energy. Electron volt, because joule we can use to measure the energy, but it is the large unit of energy. So for our convenience to measure the small energies in terms of small units, we use that electron volt. So particularly in molecules and atoms we use that energy electron volt, that is electron volt. And electron volt, so that we mention that it is not the standard SI unit of energy. That is the one of the second point. It is not the standard SI unit of energy. This is the second point, second important point in electron volt. And one more is that if the electron is decelerating through a potential difference of 1 volt, then what does it mean? Here the third point is the electron is decelerating through a potential difference of 1 volt. The electron is decelerating through a potential difference of 1 volt, then it loses the energy. How much amount of energy is lost? Is that 1 electron volt. So the loss of amount of energy, it means that is the loss of amount of energy, loss of amount of energy is that 1 electron volt. So when it is accelerating through a potential difference of 1 volt, then it gains the energy is 1 electron volt. If it is decelerating through a potential difference of 1 volt, then it lose some amount of energy. That amount of energy lost by the electron is 1 electron volt. And one more example, fourth point. The fourth point is that, for example, alpha particle. If the alpha particle is accelerating through a potential difference of 2 volts, here I am not writing full sentence, listen clearly. If the alpha particle is accelerating through a potential difference of 2 volt, then it gains the kinetic energy. It gains the kinetic energy by 4 electron volts. Example, for the electron volts, if you take the alpha particle, that is the helium particle, so if alpha particle is accelerating through a potential difference of 2 volts, potential difference is of 2 volts, then it gains the energy. The kinetic energy gained by the particle is 4 electron volts. Okay, these are some of the important points regarding the potential energy of system of charges and the unit of energy, potential energy, electron volt. Regarding electron volt, some of the points. And when it is accelerating either in uniform or non-uniform electric field, then final velocity of the particle, final velocity of the charging particle, different formulas. And these formulas we use in entrance exams, like competitive exams, we use this concept and formulas. Okay, these are very important. And the next concept, now we are going to the actual topic. That actual topic is electrostatics of conductors. So if you have any doubts, you can raise the doubts in these points. Okay, and the next one is electrostatics of conductors. Then what are the electrostatics of conductors? So to know about the electrostatics of conductors, we have one of the instruments, that is the Van de Graaff generator. Actually, this Van de Graaff generator, for theory they deleted the Van de Graaff generator, but this Van de Graaff generator we use for the practical purpose or experimentally we use to know about the electrostatics of conductors. Electrostatics of conductors, and where we use this Van de Graaff generator. First I discuss about Van de Graaff generator, just principle and how it works. That Van de Graaff generator, how it works, that I discuss with you. That Van de Graaff generator was designed by the Van de. That's why they the name came for the generator is Van de Graaff generator. He was the American physicist. He designed the Van de Graaff generator, and the use of the Van de Graaff generator, it can produce a high beam of energies. It is greater than 2 million electron volts, or we can say that about 10 raised to 6 electron volts. So that high energy, it can be produced with the help of the Van de Graaff generator. So the Van de Graaff generator we use in practical purpose or experimental purpose to know about the electrostatics of conductors. Okay, so the Van de Graaff generator So in the Van de Graaff generator, we use the sphere, metal sphere, which is having the charge, and this is having the charge, metal sphere, and one more is that hollow sphere, which doesn't have the charge, and this we are taking as the hollow sphere. So here this metal sphere having the charge, this charge we take as Q. And this charge is, and we know that electric field inside the conductor is 0 and charge also will be 0. And when this charge inside the hollow sphere, we have one more the sphere and having the charge, and that charge is transferred from this metal sphere to the outer surface of the hollow sphere. The charge can transfer. For example, here I am taking that positive charge, and that positive charge transfer to the outer spherical shell, that is on the surface of the spherical shell, because we know inside the spherical shell electric field is 0 and the charge is also 0, and there is no excess of charge inside the conductor. It resides on the surface, outer surface of the conductor. So that is the main principle of the Van de Graaff generator. The name is that Van de Graaff generator. So in that Van de Graaff generator, we have the belt. We use the rubber belt to rotate the spheres here, like wheels. And here I am using the comb. This is called the emitter comb, and it is connected to the high voltage supply, power supply. It is connected to the high voltage power supply, and this is connected to this lower belt. So, and this is connected to the motor which rotates the wheels. This lower wheel or bottom of the wheel is connected with the motor. So when the motor is rotating, and these will rotate, and the upper wheel also rotates with the help of the belt. It is like a rubber belt. And now that the voltage is passing. So here I am using, this is like a small high potential to lower potential, and here it is passing through this comb that we call it emitter comb. The voltage is passing through the emitter comb and through the belt, and one more comb we use that, which is receive the electrons or receive the charge. It's not only the electrons, charge, we can say the charge which receives the charge, and this is connected to the upper surface of the belt. Okay, now so when the electrons are passing through the belt and it is received by the comb, receiver comb, and here that it is connected with the hollow sphere, and this charge is passing through the comb, receiver comb, and it resides on the outer surface. And if the charge is like voltage is more, then here they may be ionized, the charge becomes ionized, and it can reuse that to produce the high energy, that is about 10 raised to 6 electron volts. So that is the main principle of the Van de Graaff generator. So in that we use the Van de Graaff generator. For example, imagine a sphere, and this is connected to this we imagine that Van de Graaff generator. And when the charge is passing through the Van de Graaff generator, and if you touch the Van de Graaff generator, what happens? If any person touch the Van de Graaff generator, when the voltage is passing through it, and we can observe that our hair will be in curved position, and it becomes straight and it goes in a straight position. And we might observe in movies also when the person got shocked, and particularly the person hair, we observe that it will be in a straight position. Why the people got shocked? Those persons hair will be straight. What is the reason? Because there is the electric field concept. Okay, and that electric field moves from high potential to the lower potential, that is the positive charge to the negative charge, and that charge goes into the negative side, so that it moves into the air. That positive to the negative, that is the reason the air will be in a straight and it moves in a like a curved position. And if you take the ladies like women, and if the person touches the Van de Graaff generator, we can observe clearly because they have long hair, and we can observe clearly that, and those hair will be in a curved position, like electric field lines. How the electric field lines, it moves from positive charge to the negative charge. So we might observe in the videos, when you touch the Van de Graaff generator, and the person's hair will be in a curved, straight and curved position. They will be initially it will be straight and curved position. Okay, that is the reason there the electric field it moves into the negative, so that it moves into the air position. Okay, that is the negative charge. That is one of the example of the Van de Graaff generator. So this we know the concept and how it works, the Van de Graaff generator, and we have the formula, mathematical formula for the Van de Graaff generator is that the potential difference delta V is equals to Q1 upon 4 pi epsilon naught of 1 by R1 minus 1 by R2. Okay, this is the mathematical formula of potential difference in case of Van de Graaff generator. Okay, so in competitive or in objective process we use the formula. Our intention is that how it works the Van de Graaff generator, and what is the principle? The principle is that when the inside the conductor having the charge and it is connected with the conducting wire, then the charge transfer from inner sphere to the outer sphere, which is having the spherical shell and resides on outer surface of the shell, spherical shell, and it produces that high energy beam that is about 10 raised to 6 electron volts. Okay, that is the function of the Van de Graaff generator. Okay, and with the help of this Van de Graaff generator, we can observe that we can do one experiment. We might observe that experiment in electrostatics of conductor, that is called electrostatic shielding. Okay, of conductors is the very important concept. Listen carefully. And as per the process, before going to start about the class, we should know that Van de Graaff generator. The Van de Graaff generator, actually in theory part was deleted, but we are going to discuss about the Van de Graaff generator because it helps to understand the electrostatics of conductors. In that electrostatics of conductors, one of the subtopic is electrostatic shielding. And to understand the electrostatic shielding, with the help of Van de Graaff generator, we can understand clearly. That is the reason we want to discuss anti-graph generator, even though in the syllabus it was not, but it will be helpful for the competitive part. Okay. So, anti-graph generator, what is the use of anti-graph generator and how it works? That is our motto. Because if you know the function of the anti-graph generator, then we understand easily about the electrostatic shielding. We can understand, but that is also one of the example to understand easily. That is the reason I want to discuss the anti-graph generator. So if you observe the diagram of anti-graph generator, so in the anti-graph generator there are the two wheels, and those two wheels connected with the belt is like a rubber belt, and the bottom of the wheel is connected with the motor. Here this is the motor, and the motor is rotating. When the motor is rotating, when motor rotates and the wheels are rotating and the belt will rotate. So here this first one, the bottom of the wheel is connected with the emitter we can call that emitter cone, because it emits the charge with the help of high voltage. Here we are taking at the source, high voltage source. So when we supply high voltage to the bottom of the wheel with the help of emitter cone, and the charge is passing through the emitter cone, and if you observe the diagram here, these charges are moving in upward direction, and for the upper wheel we have connected one more cone that we call receiver cone, which is receiving the charge from the emitter cone. So here the charge is moving upward direction when the belt is rotating, and here this receiver cone receives the charge and it can pass through the outer surface of the sphere, and that is the halo sphere. So inside here we have taken one more charge sphere, the small charge sphere connected here. The small charge sphere, how much amount of charge is having the small sphere, that is not the matter, but the charge flows from inner sphere to the outer sphere, the outer surface of the sphere. That is the main principle of the anti-graph generator. So here we have one doubt, how the charge transfer from one sphere to another sphere. For that I am going to take one example, simple example, to understand easily how the charge is transferred from inner sphere to the outer sphere. So here I am taking, this is the inner sphere, this is not the hollow sphere, metal sphere having the charge. For example, the charge is Q, and outer sphere is the hollow sphere, and I am taking a small example. Here the inside the sphere, the charge, suppose the charge of the sphere, inner sphere is that is Q is equals to some 10 coulomb of charge, 10 coulomb of charge inside the sphere, and outer sphere also having some charge, and the charge I am taking that for example is the 5 coulomb of charge, 5 coulomb of charge, and here the potential is that V is equals to 1000 volts. Here 1000 volts, and here the potential of the inner sphere is for example I am taking 2 volts. inner sphere having the potential is 2 volts and the outer sphere having the potential is the 1000 volts. Then how the charge transfer from one body to another body? Till we know that when these two spheres are connected with the wire, metal wire, and the charge transfer from one body to another body, till the potential becomes same. How the temperature, in case of the temperature, heat flows from higher temperature to lower temperature, and even water also flows from higher level of the tank to the lower level of the tank till the water level becomes the same because of the pressure difference. And even air also flows from high to low, that is high pressure to the lower pressure. In the same manner, here we have that inner sphere having the charge, say 10 coulomb of charge, and the potential is 2 volts, and here the potential is the 1000 volts. Then what happens here? The potential should become same. Till the potential becomes same, then charge flows from one body to another body. So now that when it is connected, here inside the conductor, we know that inside the conductor that electric field will be 0. Means that here the electric field is 0, E equals to 0. We know electric field is 0 inside the conductor, that we explain in electrostatics of conductors. Suppose here electric field is 0, that always will be 0, that I will explain you. So here electric field is 0, when electric field is 0, charge also 0, then potential will be constant. Then here the how much potential is there? 1000 volts of potential. So when 1000 volts of potential outer surface of the sphere and inside the sphere and outer side the potential, outer side of the sphere the potential will be the same. So when this potential is 1000 volts and inner sphere the potential also will become 1000. Here this is 1000 volts and at this point 1000 volts, here also 1000 volts, and here also V is equals to 1000 volts, and here this 1000 volts inside, and already 2 volts exist inside the sphere. Then what will be the total potential? The total potential is that 1002 volts. Then the charge flows from, it means that, what does it mean? Inside the sphere having the more potential, that is the higher potential, then charge flows from higher potential to lower potential. So here the charge flows from inner sphere to the outer sphere. That is one of the concepts, simple concept to understand how the charge flows from one sphere to the another sphere. So here we are supplying the high voltage of charge, and the charge is passing through the belt and it is received by the receiver comb and it passes through the outer surface of the sphere. And this Van de Graaff generator can produce high energy beam is about 2 million volt. 2 million volts. Okay, and when the charge is high voltage of charge, when that high potential, when it has high potential, it becomes ionized. Then sparks we can observe that. So when the sparks are passing, and here we have like a bone. We are taking one bone, and inside the bone the person is sitting. Imagine this is not the diagram, simple diagram I have drawn to understand about the Van de Graaff generator and how why the person is sitting inside the bone. It is like a metal, okay, metal bone. So the person is sitting inside, and here the high energy is produced by the Van de Graaff generator, and it sparks. The sparks are passing, means it strikes the bone. Then what happens to the person? Will it damage to the person by the sparks? There is no effect on the person. Okay, that we will discuss in case of electrostatics of conductors. And here we have the mathematical expression for the Van de Graaff generator. The potential difference, we have the derivation that we are not going to derive because the derivation is not that much important for the exam point of view, and even for the competitive also to use the formulas to solve the questions. Then here the potential difference, that V1 minus V2, or I am showing with the delta V. Delta V represents the change in potential. The change in potential delta V is equals to Q1 by 4 pi epsilon naught of 1 by R1 minus 1 by R2. Okay, this is the potential difference of the Van de Graaff generator. Here the notation is important. Here V1 is the potential of the inner sphere, V2 is the potential of the outer sphere, delta V is the change in potential or potential difference. Here Q1, this potential difference, we have the charges of two spheres. For example, here you take this is the inner sphere is Q1. This is the inner sphere and the outer sphere. The charge of the inner sphere is Q1 and the radius is R1, and outer sphere the charge is Q2 and the radius is R2. So now the potential V1 is the potential of the inner sphere, V2 is the potential of the outer sphere, Q1 is the charge of the metal sphere and Q2 is the charge of the outer sphere, that is the hollow sphere, and it is connected with the wire, that is the metallic wire. Then now the charge is transferred from the inner sphere to the outer hollow sphere. So then by taking the potential formulas, by simplifying it, we get the potential difference, that is Q1 by 4 pi epsilon naught. It means that the potential difference depends on charge of the inner sphere. It does not depend on the charge of the hollow sphere. Even the outer sphere having the charge is Q2, but it doesn't depend. It depends the Q1, that is the inner sphere of the charge. So that the potential difference is Q1 by 4 pi epsilon naught of the radius is 1 by R1 minus 1 by R, the difference. So by simplifying we get this formula, Van de Graaff generator potential difference. Okay, now if you come to the actual topic of electrostatics of conductors, and you might study in first chapter also some of the topics about the electrostatics of conductors. So in this electrostatics of conductors, the first point is that first one is that electric field is zero inside of the conductor. Electric field is zero. Electric field is zero inside, or we can write that inside of the conductor electric field is zero, or electric field is zero inside the conductor. So why we have written electric field is zero inside the conductor? So for that I am taking a conductor, and the charge of the conductor, suppose Q is the charge of the conductor, and we know the conductor having the free electrons, and those electrons move freely inside a conductor. Charge will move freely, that we call like electrons. Electrons move freely inside the conductor. But we are saying that electric field is zero. Why the electric field is zero inside the conductor? And to get that, and this conductor is subjected to the electric field, in that along this direction the original electric field. So I am showing with the symbol is E naught. E naught is the original electric field. So when the original electric field is applied or subjected to the conductor because of induction process. Induction process, what happens here that, and inside the conductor, and this negative charge moves towards this side and the positive charge will be other side. Positive charge is other side of the conductor and the negative charge will be other left side, and positive charge will be opposite. Because here the electric field, we know that electric field is always moves from higher potential to lower potential, and here this is the positive charge or higher potential. Here the negative charge lower potential due to the induction process, and this positive charge gets attraction by the negative charge, and here will be the positive charge. It means it will be separate. Then what will be the electric field inside the conductor? The electric field direction we know that is from positive charge to the negative charge, and here this will be the induced electric field. So when the conductor subjected to the electric field, inside the conductor induced electric field produced. And the here if you see the direction of the original electric field and the induced electric field, magnitude is same. How much electric field is applied outside of the conductor, inside also the magnitude will be the same. So then if you take the net electric field or the resultant electric field is equals to, they are in opposite direction, so E naught minus En. Magnitude wise they are same, then direction is opposite, then net electric field will be 0. This is the reason electric field is always 0 inside the conductor. So now we came to know that electric field, net electric field is 0 inside the conductor. Okay, now we got the point. Electric field is always 0 inside the conductor. This is the reason. And now by using Gauss theorem, this is the first point. And the second one is that we want to know that potential is constant. And the charge, what about the charge here? We studied the charges, properties of the charge. The charge always resides the surface of the conductor. Then to get that charge from the Gauss theorem, by using Gauss theorem, we know Gauss theorem. From Gauss theorem, we know that the electric flux enclosed by the electric flux through the closed surface, or the electric flux is equals to the line integral of electric field E bar dot ds bar is equals to the net charge divided by the epsilon r. The statement is the electric flux enclosed by the surface is equals to 1 by epsilon r times of the net charge. The mathematical arithmetic. As we know, inside the electric field of the conductor is 0. Then if you substitute in Gauss theorem, this electric field is 0. If the electric field is 0, then net charge is also 0. That is enclosed surface. It means that inside the surface charge is 0. So we know that electric field is 0 inside the conductor and the charge also 0. It means this charge resides outer surface of the conductor. Okay, there is no excess of charge inside the conductor. That is one of the point. And the second one is that the second point, the potential is constant. Potential Potential is constant inside the conductor as well as on the surface of the conductor. Then how it is that we will learn now. Potential is constant. From the first concept, we know that electric field is zero. Inside the conductor, electric field is zero. Now we want to know the potential. We know relation between electric field and the potential. What is the relation between electric field and the potential? That E is equals to minus dV by dr. This relation we know. Here from the first one, electric field inside the conductor is zero. Here also we are going to find that potential is constant inside the conductor, and that will be equal to on the surface of the conductor. Because I didn't write here that, you listen carefully. Potential is constant inside the conductor, and that will be equal to on the surface of the conductor. So electric field is zero inside the conductor. Means that E equals to 0. E equals to 0 is equals to minus dV by dr. Then dV is equals to 0. So when the differentiation is 0, when it becomes 0, then V is equals to constant. When V is the potential, then potential is constant and potential difference. Here dV represents potential difference. The potential difference will be 0. It means that inside the conductor, electric field is 0, whereas the potential is constant. And that potential is equals to the on the surface of the conductor, that V is equals to 1 upon 4 pi epsilon naught Q by R. And one more important point also is that here you see at any point inside the conductor is electric field is 0. At any point, you take any point inside the conductor, electric field is 0. Till reaches the surface of the conductor, the boundary of the conductor. It means that electric field is discontinuous. It is not the continuous. Electric field is discontinuous. So E will be discontinuous. And when it reaches to the surface, then it will be electric field on the surface of the conductor will be 1 upon 4 pi epsilon naught Q by R square. Okay, this is a very important point. Electric field is the discontinuous. Okay, now that the potential inside the conductor is 1 upon 4 pi epsilon naught Q by R. Then on the surface, this will be equals to the on the surface of the conductor is, then V is equals to on the surface of the conductor. On the surface of the conductor, potential V is equals to 1 upon 4 pi epsilon naught Q by R. Okay. So inside the conductor and on the surface of the conductor, potential will be the same. That is the constant. Potential is constant inside the surface and on which is equals to on the surface. It means that whatever of surface it is the equipotential surface. Equipotential surface. We know that equipotential surface. The equipotential surface is the potential is same at any point on the surface. You take the surface at any point, the potential will be the same. Okay, such type of surface we call that equipotential surface. So from this explanation, we can say that surface of the conductor acts as the equipotential surface. And next one, we know the properties of the equipotential surface are the characteristics of the equipotential surface. Equipotential surface and the electric field, they are always right angled to each other, and that also we do that. The third point, in electrostatics of conductors, this will be used for the electrostatic shielding, and that's why we have it. First one. The third one is that electric field is normal to the surface of the conductor. Third point, electric field is normal. Electric field is normal to the surface. So that also we show that how it will be normal. Suppose this is the surface having the charge, and the surface density of the charge is sigma. So here I am taking sigma is the surface charge density. You know the notation of surface charge density is the charge per unit area. And now we want to know that electric field, whether it is normal to the surface or not. Now I consider that the electric field is not exactly normal to the surface of the conductor. It means some angle theta along this direction. I am taking that theta. So here this will be electric field V. And here the condition is that electrostatic condition. So in electrostatic condition, see when electric field makes some angle theta to the surface, then the charges has to move along this direction. But according to the condition, that condition is electrostatic condition, which means that the charges are at rest, they are not moving. So then those charges are not moving along this component is E cos theta. Because here this resultant is E, and again resolution of vectors, and this component will be E cos theta. So that E cos theta must be equals to 0 because of the electrostatic condition. Then E cos theta is equals to 0. Then what will be the theta? Theta must be 90 degrees. Because we know that if you send the other side, it also becomes 0. Cos theta is equals to 0. Cos 90 is 0. So that theta value is 90 degrees. It means that this electric field, the electric field is always normal to the surface of the conductor. So we have taken contradiction. We feel that it is not exactly perpendicular to the electric field. So by choosing that, we have got theta is equals to 90 degrees. It means that the electric field is not with some angle theta, it is exactly perpendicular to this surface. Okay, that will be the one of the point. Electric field is normal to the surface. And one more point also, we know that equipotential surface. We prove that inside the conductor electric field is 0 and charge also 0. Then potential will be constant. If the potential is constant at any point inside the conductor or on the surface of the conductor, that surface is the equipotential surface. And one of the characteristics of equipotential surface, that electric field is always right angle to each other. Okay, based on that point, or we mathematically also we prove that the electric field is normal to the surface. And one more is that we want to find that surface charge density sigma for the conductor, and again we assume conductor, the charge of the conductor, here the charge is resides on the surface of the conductor. Charge resides on the surface of the conductor. And we want to find that what is the surface charge density on the surface of the conductor. For example, I choose the point on the surface. Here I am choosing this point. Now by using the Gauss theorem, we can choose the imaginary surface, that is the Gaussian surface. So here the charge is enclosed by this one. So from Gauss theorem, we know that line integral at E bar dot ds or E ds is equals to Q by epsilon. Q by epsilon. Then what will be the surface charge density? The sigma, we know that surface charge density sigma is equals to Q by A, and the charge is equals to surface density, charge density into the area. So their area we use that ds, then sigma into or ds. We use that S. Here also I am using the surface area into avoid the confusion. Here I am using the S. Then now if you substitute in this formula, that integral E ds, then E into the ds and taking that S. Integral ds is S. Or if you take in the form of a sphere, there it will be surface of the sphere formula we can write. And that also one of the method, or else I am taking integral ds is S. And Q, we know that sigma into S divided by epsilon. Then S gets cancelled. Then electric field E is equals to sigma by epsilon. So the electric field on the surface of the conductor is equals to sigma by epsilon. And you derive the first chapter electric field for infinite plane sheet. Infinite plane sheet, that is the non-conducting sheet, E equals to sigma by 2 epsilon. Here by using the Gauss theorem we calculated that E equals to sigma by epsilon or else. And one more, we know a sphere on the surface of the sphere, what will be the electric field in the applications of Gauss law? What is the electric field on the surface of the sphere is E equals to 1 upon 4 pi epsilon Q by R square. So as we know the applications of Gauss law, that on the surface of the sphere, on the surface of the sphere, E equals to 1 by 4 pi epsilon Q by r square, where r is equals to the radius of the sphere. Then here we can substitute that in terms of the surface charge density. We know the surface charge density is that the sigma into S. Then E equals to 1 upon 4 pi epsilon naught. Then Q we write that sigma into the surface area. We write that 4 pi r square divided by r square. Because the surface area of the sphere is that 4 pi r. Then here 4 pi gets cancelled. 4 pi here 4 pi cancel, r square also cancel. Then electric field E is equals to sigma upon epsilon naught in terms of surface charge density. E equals to sigma upon epsilon naught. This is one of the point. And the next one is that we study that electric field inside the sphere is 0 and the electric field is discontinuous and the charge is also 0. There is no excess of charge. The charge will be resides on the surface of the conductor and the electric field is always normal to the surface of the conductor. As we know the characteristics of the equipotential surface, when electric field is 0 inside the conductor, potential is constant. When the potential is constant inside the surface of the conductor, which is equals to on the surface of the conductor, it means the potential is same at any point on the surface is called the equipotential surface. And the characteristics of the equipotential surface, we know that they are always perpendicular to each other. The electric field and the equipotential surface. Or by using the method, we have taken electric field having some angle theta with the surface of the conductor, and here along this component the charge has to move, but according to the condition, electrostatic condition, the charges cannot move if they are at rest. So E cos theta must be equals to 0, then theta is 90 degree. It means that electric field and the surface are perpendicular to each other. Means normal to the surface, and the electric field on the surface is sigma upon epsilon. And next one is that electrostatic shielding. What is that electrostatic shielding? Electrostatic shielding. So here we use this electrostatic shielding to protect the sensitive instruments from the electrical influence. So for that case, we have taken the example of Van de Graaff generator. Van de Graaff generator, and here the board, that is the metal cage, and inside the metal cage the person is sitting. And here the Van de Graaff generator is producing high energy beam, and when it produces high energy beam, the sparks strikes this metal cage, but there is no effect on the person because we know that electric field inside the conductor is 0. Electric field E equals to 0. So here or else one in another way also we can discuss, that is, we know that electric field is from positive to the negative charge. How I am taking that the person can be protected from the sparks. So here this electric field, we know that electric field is from positive to negative charge. That is uniform electric field, and it moves from positive charge to the negative charge. So now what I am doing, the metal cage is placed inside the electric field because the electric field is affected on the metal cage. So here I place the metal cage. Then what happens to the electric field? Electric field cannot pass through the cage. Definitely it cannot pass through it. It will be 0. Because here see this metal cage, here the negative charge will be there, and here the positive charge and the negative charge it will be terminated. Again, upper surface of this metal cage, the positive charge on the upper surface of the metal cage. Then here the negative charge, and the negative charge and the positive charge, and again here also the electric field gets terminated. That is one way. Or we know the electric field direction is from, this is the original electric field direction, not inside the metal cage. Original electric field direction is moving from positive to the negative. Then when it is passing through the metal cage, here on the metal cage, here this negative charge, and on upper surface of the metal cage is that positive charge. Then what will be the electric field direction in the metal cage, inside the metal cage? That will be in opposite direction, positive to the negative. And this red mark shows that induced electric field. Original electric field is from positive to the negative, and induced electric field is from positive to negative. It means opposite direction, then they get cancelled. Then electric field inside the metal cage, electric field is 0. So that we use the cavities or case to protect the electrical instruments, sensitive electrical instruments from the electrical influence. Or one more example you take. If you take another example, you take the galvanometers or the voltmeters, and those meters are placed in the metal box. If you place inside the metal box, what happens if any sparks strikes the metal box, and it cannot pass through the metal box because inside that electric field is 0. And one more example also in our daily life example, if you take the lightning, at the time of lightning, if you sit inside the car, and it is a conductor, metallic conductor, and if you sit inside the conductor and the lightning cannot affect on that person, because electric field inside the conductor will be equals to 0. Okay, that phenomena is called electrostatic shielding. It is very, very important for the short answer. Okay, short answer questions, electrostatic shielding. Okay, and this we call that, this total experiment we call that Faraday cage. The Faraday did the experiment, and the Van de Graaff generator designed by the American physicist Robert Van de Graaff, and for his name, on his name they kept the name of that device is that Van de Graaff generator, which can produce high energy about 20 million volts. Okay, and this spark near the Van de Graaff generator on metal case, and on the inside the metal case the person is sitting, and it cannot affect by these sparks because electric field is 0. And this experiment, total experiment, we call it Faraday cage. Faraday cage. Okay, this is about the electrostatic shielding, and these are the topics and the points regarding the electrostatics of conductors. And these are not there in the material, but the concept based, these are very important. Once again I am recalling electrostatics of conductors. In electrostatics of conductors, first one is that electric field inside the conductor is 0. How it is 0, that I explained. When the conductor subjected to the electric field, induced electric field and original electric field will be in opposite direction, then net electric field will be 0. When electric field is 0, by using Gauss theorem, charge also will be 0. It means there is no excess of charge inside the conductor, that always the charge resides outer surface of the conductor. And the second one is that potential is constant. When electric field is 0, as we know the relation between electric field and the potential, E equals to minus dV by dr, there we prove that potential is constant. And that inside the potential is constant as equals to the on the surface of the conductor, and that surface we call that equipotential surface. and equipotential surface and the electric field are right angle to each other, or we can prove that electric field is normal to the surface of the conductor, and by taking electric field makes some angle theta to the surface, then we prove that theta equals to 90 degree. It means that electric field and the surface of the conductor are normal to each other, and electric field on the surface of the conductor in terms of surface charge density E equals to sigma by epsilon naught, or E equals to, this is one method, any method we can follow that. Generally we use this method, and this method we can prove in applications of Gauss law. In applications of Gauss law, we know electric field on the surface of the sphere is E equals to 1 upon 4 pi epsilon naught q by r square, and q is the charge, surface charge density into surface area, and surface of the sphere is 4 pi r square, and 4 pi r square cancel, remaining terms are sigma upon epsilon. And the electrostatic shielding, and that electrostatic shielding to protect the sensitive instruments from the electrical influence. So like we take one cavity, inside the cavity and on the surface of the cavity again the metal coated, like shielding, we call that electrical shield, to protect the sensitive instruments from the electrical influence. And we know the experiment also, that experiment name is called Faraday's